Okay, hi everybody. I know it's been quite a while since we did this pigeonhole principle. It's about 3 weeks now. So, anyways, let me start. Okay. So, if I say PHP, it's for pigeonhole principle. I think you understand that much. So, the first one's an obvious question. So, suppose there's a test for 100 marks, and it says that there is no fractional scores which are given, and the question asks how many students need to take the test such that there's at least 2 students with the same score. So it doesn't get any more trivial than this. So basically you need to look at the bins, and the only thing that we have to understand essentially is if the test is for 100 marks, you can get 0 marks, you can get 100 marks as well. So the total number of buckets is 101. Okay, and if you want to use PHP, then the number of students should be 1 more than this at least. So the total number of students essentially is like 102. That's the minimum number of students. So it's equal to 102. Does that make sense? Okay, so this is clearly the answer. Okay, this is straightforward pigeonhole. Now let's look at the second question. Now the question says that take a unit square, the square, which means the square is a side length of 1. I don't see why I wrote this. Choose any 5 points on it or inside the square. Again, here the assumption is that if you have the square, then the boundary of the square is pretty much not an important portion, so don't even bother about what is there on the boundary of the square. So the question is to show that they'll at least, so you're choosing 5 points, that's the clue here. So there are 5 points. Now recall standard pigeonhole. So if you have, let's say, n balls which are thrown into n minus 1 buckets, that is the minimum that you need to do to use pigeonhole, right? So if there are 5 balls, then, or 5 points or balls, how many buckets do you need? You need at least 4 buckets, correct? So that's the logic. There's a second piece also which is going to hint that. Look at it. It says that the points have to be within a distance of 1 by square root of 2 away. Okay, and the remark is only there to remind you all that this is a proof question. So that means like you can't just give me one particular example of 5 points and say that, oh, for this example there are this pair of points which are less than this distance. So that's not a typically acceptable logic. I mean, you can give me examples which are correct, but when the question is more like a proof, then you have to either show that there is no negative case possible, or there is a constructive argument to show that because of this reasoning because of this reasoning the statement is true. Okay, so you'll have to do either one of those. Okay, so the remark is no more necessary. So recall, we have 5 points. That's the clue that we have to understand here, and the square is of size 1, right? So if I have the square, and let's just divide the square up into squares of side half. Now there's a reason why I did this. Look at this smaller square inside. What is the diagonal? The diagonal is root of 1 by 4 plus 1 by 4, which is equal to essentially root of 1 by 2. Now do you see why the 1 by root 2 distance is used here? The 1 by root 2 distance is also a part of the 4 half length squares as well. So now see this, you have 4 bins and you have 5 points which are being thrown, so there'll at least be 2 points in one bin because there are 5 points and 4 bins. Then by PHP, so whichever is the bin which had, so now you can see the argument, right? So now it doesn't matter how you throw the 5 points, there's at least one bin which will have 2 of the points, and the moment you say that there is this one bin with 2 points, then the distance between those two has to be less than equal to 1 by root of 2, because the longest length between any 2 points on the smaller square is essentially the diagonal. Anything else is smaller than that straight line distance. Okay, so moral of the story is, in any of these pigeonhole principle kind of problems, or if you encounter such problems, the ingenuity is only in identifying what is the bucket and what is the ball. So once you understand that, then it becomes almost like a trivial argument at that point. Okay, so let's go to the next one. It says that I have to choose any k plus 1 distinct positive integers to show that there is at least one pair such that a minus b is a multiple of k. Oh, I think this is not difficult, right? It has to be a multiple of k. Okay. So then multiple of k means multiple of k. Okay, let me try this. Okay, so what I'm going to do essentially is, I'll take for every number, okay, find its mod of k value. So then you will have 0, 1, all the way up to k minus 1. So these will be the possible values for the remainders, right? The remainders can only be between 0 through k minus 1. So then how many buckets are there? There are k buckets. Now go back to the question. The question tells you that there are k plus 1 distinct positive integers which are being chosen, correct? So now does it make sense to say that if there are these k plus 1 distinct integers, then these are like the balls in this case, and for each one of the balls that you throw, if you find a mod k value, you have to throw them only inside any one of these k buckets. So you have k plus 1 balls, equivalently the mod of the numbers. So directly what you get by PHP, there should be there exists at least one bucket with greater than or equal to 2 balls. Now it's at this point it's very trivial, but let's just formalize that proof as well and finish it off properly. Okay, so now let us say that it is present in, for just for the sake of the argument, I'm going to say that it is present in some remainder. Let's call that remainder as x. Okay, so this one had 2 numbers. So first question, what is this number going to be? This number is going to be something of the form x plus some k times m1, correct, where m1 is an integer. What is the second number going to be? The second number, it will be the same x plus k times some m2, right, where again m2 is also going to be an integer, correct? So now look at this. I have these 2 numbers, whichever are going to have the same remainder. So if I subtract the 2, then what happens? The 2 remainders gets thrown out, right? And whatever remains here will be k times m1 minus m2. This clearly divides k, right? So that's basically the question that you are asked to show. So the whole question is to identify this bin which has at least 2 numbers such that the subtraction of them will kill off that mod, whatever is x. So it's immaterial what the value of x is, right? Okay. Oh, I think we did this one in class. So I'm going to be a little fast in this one. So the question asks you to show that you choose, I think we need 50 only for the first piece. After that, I think it's not so necessary. Yeah, I think so. Okay, so the question here says that if you choose any set of 50 numbers, you're supposed to show that there are 4 numbers such that the product of 2 differences is a multiple of 2009. Okay, yeah, now I remember this question actually. So the idea was to find prime factors of 2009. So 2009 was 7 times 260. 48, 49 is 7, which is the same as 7 times 41. So it's 49 times 41. So that's basically what is the prime factor. 741 is what it is. Okay, so now let's try and understand this question. So it's exactly similar to the previous one. Do you realize that if I want to find out something, a minus b should be a multiple of 2009, sorry, a minus b times c minus d is a multiple of 2009, then I can find something such that there is an a minus b which is a multiple of 41, and there is the c minus d which is the multiple of one is the multiple of 49, the other is the multiple of 41. So if I can show that much, then I'm pretty much done, right? So go back to a previous question. What did we say? If you want to find out something is a multiple of k, then you should throw k plus 1 numbers, correct? Are we in the same regime here? So let's start with the first one. The first one essentially wants 49, right? So if I want 49, then how many numbers should I throw? I should throw 50 numbers, which is exactly what is given in the question. Look at it. So that's a very simple, clean argument to say that if there are these 50 numbers which are thrown, then there'll at least be the set of 2 numbers. We'll just call them whichever in some bin X. Okay. Again, the whole story is exactly identical. You're going to look at mod 49. So you'll do mod of 49. So that will lead to values which are up to 48. And there is some one bin X which has 2 of these, and this is what I'm going to call as A and B. Now what I'll do is I'm going to ignore the A and B. Look at what is remaining. So I have at this point 48 integers after removing A and B. Now look at the problem. You have 48 integers. I'll repeat the same thing as binning earlier, but now what I'm doing is for these 48, I'm going to bin it up to what? Mod of 41. So that means it will essentially land into, in fact, I have 48. I only needed 42, right? But I have more here. So if I had 48 integers, then there should at least be 2 of them which will fall into another same bin. And those 2, let's call them as C and D. These 2 will be such that the subtraction between these 2 will be a multiple of 41. And that's all the question is. So it's exactly the same as the previous question. It's one slight tweak in the sense that it is asking you to use the same idea twice. So if you remember, we keep telling that when we look at these AMC kind of problems, when we go beyond the first 4 or 5 problems, either you will see like repetitions or repeated use of one idea or slightly different sequence of ideas which will lead you to a solution. So this question essentially was the same as the previous one, but the only difference here is the third one that we discussed is like a vanilla understanding problem. Like it's extremely straightforward. But the next one essentially is a small one-step tweak on top of it. Okay. All right. Okay. So the fifth one says that there are k colors which are used to paint m houses if in any configuration we consider the minimum or maximum number of houses with any single color. Oh my god. Okay, let me just forget this part and I think we all understand the question. Okay, let's try to build this question in our head. So the idea is very simple. Okay, there are m houses, correct, and there are k colors. Now what is the bucket and what is the ball in this case? We are asking for the number of houses with the same color. That means you're asking for the number of balls inside one bucket is what is the question, correct? So the bucket then should be the paint, right? So I'll have paint color 1, paint color 2, all the way up to paint color k. This is my bucket. What is a ball? Each house is a ball. So if you have m houses, what is going to happen? Each one of the houses will choose one of the k colors of paints, and depending upon whichever color that the house is going to choose, it will fall inside that particular bucket, right? So now let's ask this question, that if you had k colors and if you painted m houses, then you can have a pathological case where you actually take all the m houses and paint them in one color, right? If you do that, what happens? There are like a large number of colors which actually are not at all used. So the minimum number of houses with a specific color is not a good question to ask. Okay, so that's not a good question to ask. But on the other hand, if I look at, is there at least one color of paint which has at least so many houses? Okay, so the question is there at least one paint color used for at least some p houses? This is a very meaningful question to ask, right? Because there's no point in asking, is there a minimum number of houses for any of the paint colors? You can easily avoid that question by the previous argument that we just had. So I can ask this question, which says that is there at least one paint color which is used in greater than equal to p houses? If that is the case, what is p, right? And it's easy to say something like this, right? Suppose I equally divide. Okay, so what I'm going to do is so let's take a simple example to show this case. Let's say k is equal to 5 and m is equal to 10. Okay, then what I can do essentially is I can basically take all the 10 houses, equally distribute them so as to get two houses in each color, right? So color 1, 2, 3, 4 and 5, all of them will exactly have two houses each. Fair? What if instead of 10, if you had 12, then there is at least one house which has 3. Some other house will have 3, or on the other hand, if the same thing happens, then you can have something like all 2s, and instead of, so this is one configuration. Okay, instead of this 2s, there's a 3, so 3 2 3 2 2, so that is one configuration. Or the other option is 4 followed by all other 2s, right? So that also can give you 12. Fair? So the minimum number is 3 if you have even 12 nodes, right? So now where do you cross from 3 to 4? That will happen if and only if you have 16 of them, right? If m is 16, only then can you say that the first 15 you will equally distribute among the 5 houses to have 3 3 3 3 houses for each one of the 5 colors of paint, and the 16th house, wherever you want to put it, that particular color will have 3 plus 1, which is 4 houses, right? So what is p? P has to be something like this, right? I think you understand this, but let me just show you what I'm trying to say. Okay, so I'm saying that m by k plus 1 if k divides m, otherwise it's just m by k. So if k divides m, that is the case where we were talking earlier about m is equal to 10, for example, then it'll just be 2. That's the minimum, right? So that is like if k divides m, it'll just be m by k. But if not, what do you have to do? You will first have to remove the part corresponding to the equal ones, and then you can at most add like one house extra in one of the paint colors, because you can then keep adding just that one house in the next paint, next paint, next paint, next paint. You will not exceed that value. So how to understand that is this particular function. This is actually called as a floor function. What it does is, if there is a m divided by k which becomes a fraction or a decimal value occurs, then just choose the integer part and forget the decimal. It is not rounding, it is more like forget the entire decimal and just use only the integer part. So if it is 4.999, when you do this floor, it is still 4. Does that make sense? So if it is 12 divided by 5, 13 divided by 14 divided by 5, even if it is 14 divided by 5, you still say that from 14, right? So you remember that when we spoke for 12, we said that I could do this. For 14, what can I do? For 14, I can still do 3, 3, 3, 3, and 2, right? This still becomes 14. So I can still live with 3. So the way to do it will be to do the floor function of m by k and then add 1 to it. Okay. So this is the only question that you can actually sensibly ask in this scenario. So remember this floor function. This might be useful in I don't know, there are lots of interesting floor function related questions. There's this one very interesting math professor. His name is Michael Penn. Okay, he makes a lot of very nice YouTube videos on problems. So he has a bunch of interesting questions, and so based on this floor function. So check that out. I'll see if I can add that in the description here. Okay, let's go to the next one. This question says that there are, oh, I think we did this in class. Okay, there are 7 colors of balls in a bag. There are 77 balls of each color. I want to choose 7 sets. Okay, of each set should be having 7 of the same colored balls. Yeah, so the only tweak or only point here to remember is nobody is asking you that I should get all the 7 colors separately, correct? That is not the question. I don't really care if each one color is repeated once, twice, thrice, 4 times. I don't really care about it, right? So that's the only thing. So it just says that each set can be of any color, no restriction on the number of colors. So nobody is asking you to get 7 distinct colors and all that. No, nothing like that. Okay. So now the question is, you're blindfolded. What is the minimum number of balls needed to get the condition satisfied? So this is exactly based on whatever we did in the previous question. You remember we did that floor function kind of understanding. So let's try to build for only one set. Okay. So let's first, so step 1. If I want one set of 7 same colored balls. All right. So the idea essentially is very, very similar. So I'm going to take bin 1, bin or color 1, color 2, color 7. So these become your buckets. Now you want 7 balls, or essentially you want 7 of them to be of the same color, correct? So what is the maximum you can go? I can basically first of all drop 6 balls in each one of these buckets and then drop 1 extra ball on any one of the buckets, and that makes it 7, right? So that's the worst case scenario. Of course, there is a good scenario which you can come and tell me that I can just throw 7 balls exactly in one of the colors, but that is one specific case. It's not like a necessary condition for any way of choosing, because you're blindfolded. So there is no way to actually pick and choose a specific color from the bag, right? So for the first set, you need something like 6 times 7 plus 1, because you choose 6 balls from each one of the colors by utter sheer bad luck, then whatever happens at the end of the 42nd ball, right, is you have 6 balls for each color, and then whichever new ball that you pick of whatever one of the 7 colors it is, that particular color gets 7 balls. So done. Fair? So for one set you need, this is 43 balls. Now go back and try to remember that a minus b times a minus c should be a multiple of 2009. That question. What did we do? The moment we chose that a and b, after that we threw away the a and b and then said that whatever remaining 48 numbers, those should essentially sort of now cover for your 41 multiple, right? This problem has a very, very similar connotation. What it tells you here is the first set of 43 balls are necessary to find the first set of 7 balls of the same color. It could have happened before, it could have happened by the time it came to 43, that doesn't matter to me. But at the end of 43 balls, there is at least one color which has 7 or more balls. What you can do is, you pick any one of the colors which has at least 7 balls and take 7 of those balls outside. Call that as your set 1. So at that point, how many balls have been thrown? So at the end of 43 balls, right, there'll be one color which will have 7 balls, right? I'll just take that 7 balls out. So at that point, how many balls do you have? I have 43 minus 7, correct? So that is 36 balls plus one full set. This is what I have at this point. So now look at the same problem. Now I want to do 36 balls are currently in this buckets. How many more balls do you have to throw in order to ensure that you have one set? Again, this first set has been removed. So at this point, what is left? You have 7 buckets and you have 36 balls dropped inside those buckets. If I just throw 7 more balls, right, I'll again go back to the 43 balls. And at that point, I'll have my second set, correct? So to get my second set, what should I have done? I should basically have 43 balls plus the one set. That means I would have got my second set as well, right? So let's just make that into a table. So what are we saying is, to get set this many number of sets, number of balls. For the first one, I needed 43. For the second one, you just needed 7 more, right? So that was 50. For the third one, you need 57. That's all it is. So if you need 7 more, what do you need? How many? What do you need? So this is 43 plus 14, right? So this has to be 43 plus 6 times 7. Which is 85. Correct? 43, 42. Yeah, 85. Yeah. Okay. So I don't need to refill another new set of 43 balls here. That's the only difference here. Just like how we did that 2009 problem. There were 2 numbers which actually multiply. So let's just go back to this one. Look carefully. So here, what we did was, we saw that there were this a and b which was necessary to get to a multiple of 49. Once that a and b was found out, you throw that off. What remains is another 48 numbers, and from those 48 numbers you can actually sort of get back to your mod 41 calculations and get it, right? That's the same trick that we did here. The first set can be done at 43. Remove the 7 off, call that a set 1. It's a completed set. Throw it out even if you want, or keep it outside essentially. So you have used those 7 balls. So at this point, you have, out of 43 balls, you've used 7 balls. You need another 7 balls to get to 43, and that's basically how it goes. Okay, this is a nice cute solution. Okay, I think we did this one in class, right? This is one where there's a box which has 200 balls, it seems. There are, what is given here essentially is, it says that there are 60 red, 60 green, 60 blue, and the rest are either white or yellow. So what has happened here is, I have no idea whether it is white or yellow. That's basically the unknown here, right? Or it could have been 10 and 10, it could have been any number in the middle. So nobody knows how or what that number is. So that's what I've written here, saying like I did not specify anything about whether it is white or yellow balls. Yeah, I know. So the question is, how many balls do we need to ensure that there's at least 20 balls of the same color? By now you must be like sort of savant at this, right? But the only difference between the previous questions and this question is, so let's say, for example, let's just take this example now. Let's just say that it did not have 200 balls. Let's say that this part was not there and this was not 200. Let's say it was 180 balls. If it was 180 balls and if you needed 20 of the same color, what would you have done? It was very straightforward, right? At this point, what is the worst case that can be done? I can take all the three colors, red, green, and blue, put 19 balls in each, and then add just one ball, and then the moment you add that one ball, you get the 20. So that means 19 times 3 plus 1 equals 58. This is the minimum number of balls that you might need to ensure that in this 180 balls, you definitely will have 20 of one color. Now let's throw this wrench back in. So the wrench essentially is like, what happens if these extra 20 were there? The difficulty is these extra 20 will not at all count for an exact value of another 20, right? And we never know whether the number of whites was 20 or whether it was less than 20. So there's practically no way of doing anything. So if you want to ensure that something is true, look at it. It says that ensure that there is at least, which means irrespective of how many yellows and how many whites were there, you should give me a number which will make sure that there is at least 20 balls. In that case, you just take 58 and add the 20 extra balls. It doesn't really matter at this point, because what would have happened if from among that 58 balls, right, if I did not pick that white or yellow at all, then by the end of 58 itself you would have got it. But suppose, for example, you kept having some or the other of these bad balls, which is the white and the yellow balls in the middle, how many will be the worst case or the most disruptive if you're suppose picking all the white and yellow balls, all the 20 of them in the beginning, and then only you start this whole process of picking red, blue or greens, again by some really sheer bad luck. Then even at that point, the 20 plus 58 will ensure that you have at least 20 balls of one color, which is red, blue or green. Okay. All right. I'll come back to doing, so I kept telling all of you that we would like to do some kind of coding exercise and stuff like that, right? So I'll try to do this birthday paradox as a coding problem for you, because I don't want to do a proof at this point. It's doable, but let's do a coding exercise with this. It might be interesting, and it might be, again, let's see, it might be interesting. Okay, so this is a classic puzzle actually. This is one of those classic puzzles which is given to any combinatorics, graph theory class in first any undergrad puzzle book that you see. You might find this kind of problem, because there's this one cute little constraint that will throw everybody off easily. So let's try to build and understand what this question is. The question says that you have to draw a graph with n vertices. Okay, if you have n vertices, what is the meaning? Let's say, for example, I'll start by drawing a graph with 4 vertices. Okay, if you have 4 vertices, then what is the only constraint here? You can basically have 1, 2, 3 edges out of one node. That's the maximum you can have, because we are not, so look carefully. So what it says is that you cannot have a loop. So the first constraint is there is no edge which start and end at the same vertex, and for the same pair there's at most one edge, which basically means that I cannot I cannot build an edge like this, or I cannot say that there is this one and that one both connecting the same pair of vertices. So if none of that is allowed, which is basically the interpretation of what is called as a simple graph, then if I have nodes 1, 2, 3 and 4, then the maximum number of edges out of any node will be n minus 1. Clear? If there are 4 nodes, then starting from 1 I can go to 2, 3, 4, 5 all the way up to n minus 1, right? The same thing, if you start at any other node, you can always go to all the other n minus 1 nodes, right? What is the minimum number of edges? Let's ask that question. If suppose I had a graph like this, right? So then what about node number 3? How many edges does it have? Min number of edges out of any node is equal to 0, right? Does that make sense? Because you can always pick one node and never connect that particular node to any of the other nodes available. Again, I'm using node and vertex interchangeably. They are the same, they mean the same thing. So look carefully. So at this point, so what is all the possible number of edges out of any node? It can go from 0 to n minus 1. And the number of, so that's what, so the question essentially is asking you, look at the question. The question asks you to show that at least 2 vertices will have the same number of vertices going into them. Okay, whether it goes into them or out of them, it's exactly the same interpretation. Okay, so I assumed that the vertex was going from 1 to 2, 1 to 3, etc. They're saying that here it means like, you can always say that this is all going into one. At this point, I think all of you understand it doesn't really matter. Fair. So now, what are the buckets? The buckets are essentially the number of edges into a node. Okay. So it can either be 0, 1, all the way up to n minus 1. So how many buckets do you have? You have n buckets. What are the balls? The balls are essentially the nodes, right? So the nodes will be balls. How many nodes do you have? You have n nodes. This is basically what is the only point of contention here. So there are n balls or n nodes and there are n buckets. But the moment you come to this kind of situation and we keep getting confused as to pigeonhole implies like the number of buckets should at least be 1 less than the number of balls that you throw, right? Otherwise, I don't see a chance of doing a pigeonhole here, correct? So where is that one piece which is gone? So that's basically where you have to apply your logic, okay? So look at this picture again. When I drew the first example where I said that there was this one node, let's call that as node number 1, which was connected to all of the other nodes, then is it possible that there is one node which has a degree of n minus 1 or which has n minus 1 edges going out of it, and there is another node which has a degree of 0, which is to say that are these two things simultaneously possible? It's not, right? Because if there is some node which has no edge going into it, like if this is true, if no, so take this example. Suppose node number 3 fell here. Then is it possible to have any node having all the n minus 1 edges? No, right? None of the nodes will be able to connect to node number 3. So automatically all of them will have at the most n minus 2 or less than that number of edges only, no more than that. The same way in reverse, if let's say for example, if there was this one node which had all the other nodes connected to it, that is it had all the other n minus 1 edges going out of it, then that means there is nothing which can actually have a 0 edge into it, right? Because that one super node, let's call that as node number 1 in this example, that super node essentially is getting connected to all of the other nodes, which means if this particular thing is true, then this is false. The other way around, if this is true, then this is false. So now you understand that yes, there are n buckets possible, but because of the special way in which we actually choose these edges, right, all the n buckets can never work at the same time. So ideally it says n, but there's only n minus 1 which can be used for any graph that you draw. So if you draw any graph, there's only n minus 1 buckets that you can use. You cannot have a graph which will use all the n buckets that we defined as the number of edges. So the moment you show this point, right, then you are in classic pigeonhole, because now you have n nodes, n minus 1 buckets. Then the question is obvious. So all you're asking essentially is, if you throw n balls into n minus 1 buckets, there'll at least be one bucket which will have more than 2 balls, which is also another way of saying that there'll at least be one pair of nodes with the same number of edges outside it. I think I borrowed this question from the book only. So there's nothing interesting in this question. It's only a computation question. There's no logic in this question. So there's a deck of n cards with the number of sets of 6 cards. So the number of sets of 6 cards. So the moment you say that you're counting sets, then are you counting with repetition? Sorry, with order or without order? You don't need to bother about the order, right? So now this is a combination question. So what it says is, n choose 6, which is the total number of sets of 6 cards, is 6 times that of n choose 3. That's all is the question. So they're asking you to find what is n. So now it's only a question of computation. So let's do it. So what is the left hand side? This is n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 divided by 6 factorial is equal to 6 times n minus n times n minus 1 times n minus 2 divided by 3 factorial. Correct. This 6 and 3 factorial can be thrown out of the window. n minus 1 n minus 2 can be thrown out of the window. So what you get? You have n minus 3 times n minus 4 times n minus 5 is equal to 6 factorial. 6 factorial is 720. So at this point, right, you have to be very smart about trying to choose what you want to sort of build from here. So you want to get to a product of 3 numbers, which is 720, correct? There is this very simple idea to understand that 9 cube, right? 9 cube is 9 into 9 is 81. 81 times 9 is 729. So I am almost around the 9 cube mark, if you realize. So that itself should give you a big hint. So 8 times 9 times 10 is a simple answer, correct? So 8 times 9 times 10 is equal to 72 into 10, which is 720. So this is 8, this has to be 9, and this has to be 10, right? So that means n is 13. Don't make this mistake of coming and saying that n minus 3 is 8, n minus 4 is 9. I mean, doesn't make sense that way, okay? So don't say that it is 11 by choosing the n minus 3 equal to 8. Okay, so you have to be a little careful about that. That's the only catch here as well. That's all. Okay, the last one. There are many solutions to this particular problem, okay? There is this one very simple, very easy, understandable solution. So let me try to show that. So the question asks that if there is a set of n integers, okay, then there is a subset of them such that the sum of that subset is a multiple of n. Now you all know that if you have n numbers, right, the total number of subsets is 2 to the power n. Now one can immediately argue something like, okay, if I have 2 to the power n possible subsets, can I then immediately say that all the possible 2 to the power, I mean, let me say it like this, okay? So for each subset, so n elements implies 2 to the power n minus 1 subsets. Why did I say the minus 1? clearly the empty set has to be thrown out of the window. Okay, if you say empty set and I'm not going to choose any number, it doesn't make any sense. Okay, so let's say that I have 2 to the power n minus 1 subsets, and now you want to show that there is this one subset which is actually having a sum which is a multiple of n. Now, having this very large number of subsets is good. I'm not saying it is bad, but how does that lead you to what is the sum of that subset? That's not immediately visible, in the sense that, let's take this example of the set being 1, 2, 3 and 4, and I want to look at all these subsets, all the subsets of size 2. Okay, all subsets of size 2. So what all do I have the sum as? So I'll have 1, 2, 3, 4 with 1, 2, 3, 4. So the sum here will be 3, 4, 5. But then 2 with 3 will also be the same, 5, 6. 3 with 4 will be 7. So the total number of options will be 3, 4, 5, 6, 7. So you see that the 5 repeats. So not all the 2 to the power n minus 1 will have unique values of subset sums. That's the first question. So how can I use that is something that we don't know very clearly. So there is something which you can tweak around the number of subsets and go around, I believe, but there is a simpler approach. Like at this point, it's clear that I cannot look at enumerating all possible subsets and going from there. So let's try a different approach. So what do I need to do? I want to show that there is something which is a multiple of n, right? So then if it's a multiple of n, then from the first problem onwards, what have we been doing? We've been trying to get this modulo of n. And the moment you do modulo of n, then how many buckets you have? You have buckets which are n buckets. So let's do the same thing. So I'll do something like 0, 1, etc. up to n minus 1. So this is the mod of n. This is the way I define my buckets. Now what is left essentially is I have to now define how do I choose my balls. Okay, so let's ask this question. So let's say that the set of n integers, right, this set, right? So I'm going to define this set as a1, a2 all the way up to an. Okay, so what I'll do is I'll first start with a1 mod n. It will fall somewhere, wherever it is. Just for the example, I'm saying it is falling in 1. The next thing that I'll consider is I'll do a1 plus a2 mod n. Where will this fall? This will fall essentially in some other bin, and it will keep going. Let's say, what do I have last? So the next one will be a1 plus a2 plus a3 all the way up to a1 plus a2 plus all the way up to an mod n. Okay, so now look carefully at this. This is going to use at least the same answer as that. You remember this graph problem? There were these two extreme bins which are not interesting. Okay, so this bucket problem has the same kind of thing. So understand this. I have this n minus 1 buckets, correct? Sorry, I have n buckets because I'm doing modulo n, right? If there is any one of these elements which actually falls inside bucket 0, no? If it falls inside bucket 0, then that subset is enough. That sum is perfect because it has a modulo with n is 0, which means it's basically a multiple of n. So if any one of these n numbers falls inside bucket 0, then the problem is trivial. It is straightforwardly solved. If it doesn't, then what is the meaning? So if none of these n sums fall into bucket 0, then they fall into how many buckets? They only fall into at the most n minus 1 buckets, which are like buckets numbered 1, 2, 3 all the way up to n minus 1, correct? So now we have pigeonhole. We have n sums, right? Starting with a1, 1 and 2, 1, 2, 3, etc. up to 1 to n. So there are n sums falling inside n minus 1 buckets. So that means there should be at least one bucket which will have more than one, right? So whichever bucket has that 2, you take that. Let's take this example as if like this one and then this one. Let's just take this example that these two essentially fell into the same bucket. If that is the case, then what I can do essentially is you take from these two, throw this a1 plus a2 plus a3 out from this bottom sum. That is like whatever you have as the bigger value, right? Subtract the smaller value. So a4 plus a5 plus something all the way up to an should essentially divide n. So mod n should be equal to 0. Right? Because you've taken that a1, a2, a3, which is having the same remainder as that of a1 through an. So if you just remove that portion which is corresponding to that remainder part, you are pretty much going to land up with this sum, which is from a4 to an, which will essentially multiply n. Okay. The last problem, maybe we'll talk about it separately sometime when we meet, and I'll try to write a code when I meet you guys for the for that what's that called, is that birthday paradox problem. All right. Okay, I think I'm done. Have a good week. See you.